Hi everyone. Welcome to part 1 of a lecture covering plasticity. In this lecture, I'll describe the mechanisms that occur over a wide range of length scales in metals that give rise to inelastic behavior. In an early lecture, I described the stress-strain curve as it actually manifests in reality. The behavior extends from being elastic and recoverable up to the yield point where plasticity is observed. This observed behavior was quite contentious in the physical sciences at the beginning of the last century. Theory back then could only account for strength on the basis of bonding energy, and therefore the theoretical strength, based on breaking all of the bonds all at once, was much higher than the point where plasticity was observed. This isn't to say that there were competing theories as to why there was a discrepancy in the late 1800s and early 1900s. However, these remained theories until experimental confirmation could take place. Let's examine what is the cause for the discrepancy between theory and reality. Consider the following 2D arrangement of atoms, notionally in a simple cubic arrangement. Can you spot anything wrong with it? Here, let me put some grid lines showing the cubic arrangement. If you didn't notice it already, there is a fault in the center of the arrangement of the atoms. It can be described as an extra half plane of atoms that has been inserted in this local region. On the upper half of this arrangement, which contains the extra half plane, the atoms are closer together horizontally, immediately proximate to the extra half plane, and gradually increase in distance to some mean separation away from the fault. This extra half plane of atoms is known as an edge dislocation. It has a symbol which represents its shape, an upside-down T. Dislocations are quantified by two parameters, which I will describe subsequently. We can convey both an orientation of this fault along with its magnitude in the following way. Using the convention of clockwise and finish to start, we draw a circuit around the dislocation, as shown by this blue line. We paste the same number of atoms down, horizontally, back up again, and horizontally once more. Here I've gone down by 5 atoms, left 8, up 5, and right by 8. Note that we do not end up at the same location where we started. The distance needed to complete this circuit around a dislocation is called the Burger's vector. The magnitude would be 1 lattice spacing, and the direction would depend on the convention employed to render the circuit. If one were to use my convention of clockwise and finish to start, the Burger's vector's direction would point left to right. This exercise may seem a little artificial, and it may not be immediately apparent why it's necessary to define and employ a Burger's vector. Let's back up a bit. How are these dislocations able to manifest in the first place? Well, right from initial solidification, there are plenty of opportunities for these types of packing faults to occur. Here I've shown a few with some gross simplifications. First, alloy ingredients or contaminants may locally change the packing density, as shown by the red point, providing the opportunities highlighted by the 2 uppermost red arrows. Next, vacancies can also occur as well. These can be in the middle of the lattice as indicated by the dashed line, or towards the edges of a grain. Sites for dislocations highlighted with the 2 bottommost red arrows. The reason why there's a discrepancy between a theoretical strength of metals and how they actually present themselves is because crystals are imperfect. They contain dislocations, a great deal of them in fact, right from where they first solidify. As will hopefully become clear over the next lecture, it becomes possible to strengthen or weaken a metal by altering it in a way to make movement of these dislocations easier or harder. Before we do so, let's look at another form of dislocation. Consider the following lattice, again made of nominally simple cubic unit cells. What I've depicted here is a cube and twisted the top half relative to the bottom half, so that one quadrant has shifted back by 1 unit cell spacing, with the spacing diminishing moving back into the cube. Drawing the arrangement on plane ABC, we end up with a configuration on the plane which contains this shift to the right. Even though I've shown the fault manifesting on the surface of an isolated cube, this type of fault often appears internally within crystals. we can apply the same technique as before with the edge dislocation for quantifying orientation and magnitude. Let's do the same thing as before, where we draw a circuit around the fault. The core of the dislocation is not as readily identified as an edge dislocation. I've cheated a little here with my depiction. It actually appears somewhere slightly to the right of point A along line AB. In this instance, I've gone counterclockwise with my circuit, but the relevance to the magnitude of the Burgers vector associated with this fault is the same. It's still the difference between the start and end of this circuit. This is a screw dislocation. It differs significantly from the edge dislocation on the basis of its Burgers vector. Note the 90-degree shift in orientations between edge and screw. We'll show this next with a mixed dislocation. Here is a combined screw and edge dislocation, both with a parametric and planar representation. On the front face of the domain, it starts as a screw dislocation proximate to point A, and then wraps around point B to end up on an edge dislocation at point C. Geometrically, its construction would be considered the same as that for a screw dislocation just shown, but the extra half plane that would otherwise extend out of the back of the cube has been constrained, and therefore appears as an extra half plane of atoms above the plane ABC. Simply by inspection, we can identify the Burgers vector on the screw side, AB, and on the edge side, BC. Since this is a continuous dislocation, it must smoothly blend between the two. Additionally, it must also have nearly the same Burgers vector magnitude as it does so. So why is the Burgers vector important? Well, the magnitude has significance on a crystallographic and fundamental physical level, the subject of which is beyond the scope of this course. What is in scope is that dislocations can move, and the Burgers vector identifies the direction that this occurs. For screw dislocations, they move orthogonally at right angles to the Burgers vector, while edge dislocations move parallel to the Burgers vector. Let's now look at how an edge dislocation can move. Let's start with a small section, which initially starts as being fault-free. If I apply some shear to this small section, evenly across the dashed line, I disrupt the local metallic bonding of the first column of atoms. Note that shear is the only way for this to happen. If I keep applying some shear, then the same thing happens to the next column of atoms about the plane where I am applying my shear. The first column reassumes a bond as best it can. This leaves a column of atoms hanging between the two other columns. We've created an edge dislocation. If I keep pushing, the same thing happens again, with this extra half plane moving along. My dislocation continues to move. Finally, if I reach a free edge in 2 dimensions, or a surface in 3 dimensions with my half plane, then the dislocation is eliminated. But if it stays contained within the lattice, then we've just moved it around, so it may appear as depicted earlier. What's important to appreciate is that this edge dislocation moves parallel to the Burgers vector. The direction it will travel in is dependent on the direction in which shear has been applied, either right to left or left to right. These dislocations are everywhere in crystals, but are hard to see experimentally. If one has a transmission electron microscope and a thin enough section, then they can be observed directly, as shown here. On the left is some nickel showing a series of screw dislocations. On the right there is another foil which is showing a much more chaotic arrangement of mixed dislocation types, both edge and screw combining. What do these dislocations have to do specifically with the yield stress? The stresses required for dislocations to move, or glide, is tens or hundreds of megapascals, orders of magnitude lower than what is required to shift entire planes of atoms past each other. The nature of the decentralized metallic bond, plus these dislocations, make it such that not all bonds have to break in order to move. You only have to move singular atoms. The yield stress can be strictly defined as the stress where dislocations start to move. It may seem that the more dislocations a crystal has, that is, the total length of dislocations per unit volume, then the easier it would be to deform. This is not the case. It is more complicated as dislocations can interact, something we'll cover when discussing strengthening mechanisms and strain hardening. So in this part, we've covered the reason why the theoretical strength of metals is much higher than reality. This is due to flaws in crystallographic arrangements called dislocations. We've covered the two different types of dislocations, edge and screw, as well as how they can combine to form mixed dislocations. I've shown how an edge dislocation moves parallel to its Burgers vector, and I've described that screw dislocations move orthogonal to its Burgers vector. In part 2, I'll detail this topic further and couple it to phenomena which is observed at longer length scales. Until next time.